Dear students, welcome back. So we have already started laser, and in the previous class we had done we had learned about the coefficients of the Einstein coefficients. That is the interaction of radiation with matters, and there we had seen the three types of the coefficients which was proposed by Einstein. Now in this class we are going to look into the relation between those Einstein coefficients. So relation between Einstein coefficients. So we have three type of the coefficients. First coefficient we call as A12. Let me take with the marker. First coefficient is called A12. Second is called B12, and third is called B21. Just to review you. So what we had done, that we had taken the two energy states. First we had called as the ground energy state. So let us suppose we had called as this is or E1. And another, the excited state, we had called as E2, and we had taken in E1 and E2 we have the N1 and N2 number of the atoms respectively. That is, here we have the N1 number of the atoms, here we have the N1 number of the atoms, N1, and here we have N2 number of the atoms. Here we have the N2 number of the atoms. So if you are going to, here we have, let us suppose here we have the atoms. So these are your N1 number of the atoms. At the thermal equilibrium positions, most of the atoms will be in the ground state. Here also let us suppose we have some atoms, right, at the thermal equilibrium positions. Now the firstly we say, if you are going to give any radiation to this, right, so any photonic energy we are going to give, and we are radiating with the photonic energy to this atom, then this atom is going to absorb this photonic energy and it is going to move up to the excited state, and this coefficient we have called as B12, and it is called your absorption coefficient. This is called your B12. Now the second I call, that is the atom, those atoms which has gone there, which is in the excited state, will come back to the ground state automatically without any radiations, and then so this is called your spontaneous emission, and this coefficient we had called as A21. This we had called as A21, not A12, A21. And the third coefficient we had called that if you are going to radiate this atom with the photonic energy, so now in the excited state we are going to radiate the atom with the photonic energy, and then it is coming back, right, to the ground energy state, and that coefficient we had called B21. So we are going to have the relationship between these coefficients, that is A21, B12 and B21, right? So let's look into it, and let me delete all these extra things that I have written, and so that we can understand with the clarity. All right. Okay, so let's proceed. Let us consider an assembly of the atoms in the thermal equilibrium at the temperature T with the radiation of the frequency nu, that is the frequency that we are giving is nu, and energy density is U nu. So total energy that we are providing to the medium is your U nu, and in the ground energy state and the excited energy state we have N1 and N2 number of the atoms, and we had discussed. The probability of the absorptions, that the number of the radiation in the state 1 which can absorb the photons and rise to the state 2 per unit time is given by, so this is called probability of absorption, so P12. So first is called your absorption, which is directly proportional to the number of the atoms in the ground energy state, and it is also directly proportional to the energy density that we are giving, right? And therefore this is your proportionality constant, and we call B12, and this is your first case, that is your absorption. We also call this is a stimulated absorption. So P12 is equal to your absorption, right? So P12 is equal to N1, B12 U nu, and this we are calling as equation number 1. Now we are coming to the next one, the probability of the emission. Now we have the two type of the emission. One is coming by the spontaneous emission, and another is coming by the stimulated emission. So this is your spontaneous emission, this is your spontaneous emission, and the second one is your stimulated emission. So total emission is equal to your spontaneous emission plus stimulated emission. Spontaneous emission is only directly proportional to the number of the atoms, because you are not going to give any energy to this, and stimulated emission is directly proportional to the number of the atoms N2 and the energy density that you are providing to the atom, right? So we have added both of them. So this is your total emission. So in the previous case we have seen the total absorption, and this is your total emission. Naturally, at any thermal equilibrium position, right, absorption probability will equal to your emission probability. So in the equation 1 we have calculated P12, and here we have calculated P21. So at the thermal equilibrium position, what we are saying, P12 is equal to P21, and therefore we have equated the equation number 1 and equation number 2. So by equating equation number 1 and 2, we get N1 B12 U nu equal to N2 A21 plus N2 B21 U nu. So here I have multiplied by N2 to both the factors. So this is your at the thermal equilibrium positions. Now what we require to do, we require to solve this to find out the energy density U nu. So what we require to do, we require to solve this equation and find out the energy density, and this is what we are going to rearrange this equation and solve. Alright, so just we are going to rearrange. So from the right hand side we have taken the U nu on the left hand side because we have to calculate the value of U nu. So the previous equation we have just rearranged, right, and U nu I have taken common here. So this is the value then we are getting. Then further if you go, so U nu can be given as N2A21. So this is your right hand side, N2A21 upon N1 B12 minus N2 B21. This is the value of your U nu, right? Now what we can do here, we can divide both the denominator and numerator by the value of N2. So here also we have N2, here we don't have N2, so we can divide this, so it will become N1 upon N2, and this N2 and N2 will get cancelled, right? So we have divided all the terms by N2, and therefore we are getting this equation. This is the equation that we are getting, right? Now further what we have done here, I have taken B21 common. What we have taken, B21 we have taken common. Why we have taken common? Because we want to bring this in terms of the blackbody radiation, the equation for the blackbody radiation, the detail about which we'll understand in the quantum mechanics. So what we can say, U nu, by dividing by taking this value common, what we can say, A21 upon B21 we have taken common, right? So naturally we are going to divide by B21. So N1 upon N2, B12 by B21 we have taken, and here we don't have anything, so it will get cancelled and you are getting -1. So this is your just a simple simplification of this. All right. Now Einstein has proposed, this is important, that at any thermal equilibrium position, the probability of the absorption is going to be the probability of the emission, right? Then that is B21 will equal to your B12. These two probability are going to be equal. So what we can do over here, B12 equal to, we can write B21, and then what is the equation we can say? So here of course this will get cancelled. So what we are getting, A21 upon B21 N1 upon N2 -1, and this is your equation 3. Now we are going to substitute the value of N1 upon N2 by using the Boltzmann law. Boltzmann law of distribution of the atoms. So first let us understand what is the Boltzmann law of the distribution of the atoms. From there we are going to calculate the N1 and N2, that is N1 upon N2, and going to substitute that value here in the equation 3. So let us see this. So Boltzmann distribution law of the atoms says, let us suppose we have different number of the energy state. So we, as I had told you in the previous class, we have the infinite number of the energy states, and the atoms are going to be distributed in such a way that always in the lower energy state, the number of the atoms will be higher than the upper energy state. So this is how the atoms are distributed. So let us suppose if you have 100 atoms, just for example, roughly just I'm telling you. So here we can have 50 number of the atoms in the first, then here maybe we'll have the 30 number of the atoms, right? So this makes your 80. Here we can have let us suppose 15 number of the atoms, and then again what is left out, whatever is left out, let us suppose here we have, and this is your 5 number of the atoms. So what we are finding, the number of the atoms is gradually decreasing as we are moving from lower energy state to upper energy state, right? So what we are finding, this is your exponential relation, right? This is your exponential curve. So this is what This law was given by the Boltzmann in the relation with the temperature and the energy. So let us suppose here this energy is your E1. This has the energy E1, and you have the N1 number of the atoms. This we are calling as E2, and again here we have the N2 number of the atoms. This we are calling as E3, and here we have the N3 number of the atoms, right? So like this, and the total number of the atoms is your N0. Total number of the atoms is your N0, as here we have taken 100. 100 is your total number of the atoms. So with respect to this, the Boltzmann has calculated that in a particular energy state, how many atoms can be there, right? And that is called the Boltzmann distribution law of atoms. He said, in any energy state, let us suppose we are calling as E1. This is your energy state in which we want to find. This is your E1. So number of the atoms in the energy state E1 will be equal to N0, where N0 is your total number of the atoms, exponential E1 upon KT. Whatever is the value of the energy of your E1, that value upon K and T. K is the Boltzmann constant, right? And T is the temperature, right? So N1 equal to N0 exponential minus E upon KT, right? So similarly, if I'm saying that what will be the total number of the atoms in the second energy state E2. So in the E2, what we can say, number of the atoms in E2 will be equal to N2, and N2 will equal to N0 exponential minus E2 by KT, because its energy is E2, right? Here the energy is your E1. So here I have already shown you. So what we can say, N2 is equal to N0 e to power minus E2 by KT, where N0 is your total number of the atoms. Now what we can do? We can do the simple, simple solution of this, and we can divide this N2 by N1, and we can solve, and then we can substitute the value of N1 upon N2 in the previous equation. So this is what we are going to do over here, right? Let me erase this. All right. So I hope now you will able to understand. So this is what I have done, N2 upon N1. This is what I have written. So this is just as simply I have substituted the value. So N2 upon N1. So this value I have taken up, right? This value I have taken up over here. So it's a very simple just calculation. So N2 upon N1 equal to exponential minus, I have taken common. Here it is your plus. So here I have made it minus, because minus minus become plus. So what I can write, E2 minus E1 by KT. So what will the value of N1 by N2 upon N1? N2 upon N1. Now E2 minus E1 we are calling as the energy difference between that two energy state, right? And that we are calling delta E, and delta is equal to what? H nu. So this is the value that we have substituted, where E2 minus E1 is the energy difference between two energy state upon KT, right? So this is your value of N2 upon N1. Then what is the value of N1 upon N2? Just you reverse it. So this minus will become plus. So N1 upon N2 equal to e to power H nu upon KT, and this value is required to be substituted in the previous equation 3 that we had calculated. So let's substitute. Right, so this is your equation 3 that you had calculated. This was your equation number 3 that we had derived. So here I require to substitute the value of N1 upon N2 that we have just calculated. So what we have calculated, N1 upon N2 equal to e to power H nu upon KT, right? So this is your energy density that we have calculated. So energy density here we are saying U nu equal to A21 upon B12 e to power H nu upon KT minus 1. Let us suppose I am calling this equation as your fourth equation, right? This is what? This is your energy density. Now Planck has calculated what will be the total energy radiated through a black body, right? The detail about this we'll discuss again in the quantum mechanics. Maybe we'll see this derivation also, how this derivation has come. But right now let us see just that derivation. So the energy which is going to be emitted from a black body cavity, right, is given by 8 pi h nu cube by c cube 1 upon e to power h nu upon KT minus 1. And let us suppose this is your fifth equation. This has come from your black body radiation. How it has come, that I will again explain you in the quantum mechanics, and there we'll see, right? Now what we can see here, this is also your total energy density, right? And this is also your total energy density which is coming from your black body cavity. So naturally here these two equations we can equate. So equation 4 and equation 5 I can equate. So if I'm going to equate the equation 4 and 5, then the coefficient of this term, right, is 8 pi h nu cube by c cube, and coefficient here we can say 1 upon this value is your A21 by B21. So if I'm going to equate these two, so what I can say, A21 by B21 equal to 8 pi h nu cube by c cube. This is your A21 by B21. So now this is the value, right, of A21 by B21. All right. Now we can use this expression to find out how we can amplify the light. So here what we can say, A21 by B21 is directly proportional to nu cube. That is frequency that we are giving on the for the radiation, right? So that is directly proportional to your nu cube, because all other things are constant, right? So A21 by B21 is directly proportional to the nu cube, right? So we have got two expressions. One expression is over here. This is your energy density, your equation number 4, and this is your another equation that we are taking here. All right. So now let us proceed for how we can amplify the light, because in the laser our main aim is to amplify the light. That is light gain we have to find out, right? So what we should do so that we are able to amplify the light. So for that we have the three types of the atomic emissions. One was your absorption, through which the light was going from the ground energy state to excited energy state. Second was your spontaneous emission, by which the light is coming from the excited state to ground energy state. And the third is your stimulated emission, where you are going to give the radiation, and then with the interaction of that radiation, the light is coming from excited energy state to ground energy state, and the photonic energy is being released in the medium. So naturally, whenever the photonic energy is getting released in the medium, that photonic energy is required to be amplified. So this is what we have to see. Under which condition this photonic energy can be amplified. We had already seen that in case of the spontaneous emission, we cannot interfere or superimpose these waves, because they are highly incoherent. They are not in the phase, they are not the time dependent, they are completely random. So photonic energy which is being emitted by spontaneous emission cannot be superimposed. Absorption, there is no case of the superposition, because you are giving the energy from outside. So what is left? What is left is your stimulated emission. So naturally we have to use the stimulated emission to amplify the light, or to make the gain in the light. So what we should do according to your previous equation, so that the light is getting gain, or will have the gain of the light by spontaneous stimulated emission. So if what we require to do, we have the three type of the interaction. One is the absorption, second is your spontaneous, and third is the stimulation. It does mean absorption and spontaneous should be minimal, and stimulation should be maximum. Then only you will have the maximum energy density available in the medium, and you are able to amplify the light. So this is what we have to understand. What we should do so that we are going to get the amplification of the light, and this is what we are going to look into. So what we are saying, at the thermal equilibrium, the ratio of the stimulated to spontaneous. So let us see what is the ratio of the stimulated to spontaneous, and then we'll understand how we can increase the stimulated and how we can decrease the spontaneous. So this is been given by what we can say, stimulated emission upon the spontaneous emission. So stimulated emission is directly proportional to the number of the atoms, which is your N2, and energy density U nu. And spontaneous emission is only directly proportional to the number of the atoms N2. Here B21 and A21 is your constant, right? So what we can do, so just we have solved this, whatever is the common factor that we have cut on both these side. So what we are getting, B21 upon A21 into U nu. What we are getting, B21 U nu upon A21. So what we can say, it suggests that in order to enhance the number of the stimulated transition, the radiation density U nu is to be made larger. So what we require, if this value is going to be larger, right? So naturally this value of the stimulated emission is going to be larger, right? And spontaneous emission will be less. So what we require to do, in the medium we should have the very high photonic energy. If there is a very high photonic energy, then we have the more chance of the stimulated emission and less chance of the spontaneous emission, and that is our aim. So what we require to do, we have to take care that there is a sufficient photonic energy available in the medium to enhance your stimulated emission. This is your one condition. The second condition, the ratio of the stimulated to absorption transition. So again, one is your stimulated emission and that is your stimulated absorption. Absorption, the atom is going from the ground energy state to excited energy state, and stimulated emission, it is coming from the excited state to the ground energy state. But in both the cases, we are giving the radiation with the external photon. All right. So let us see what we are saying. Stimulated transition upon spontaneous transition. All right. So here we are taking stimulated and spontaneous. All right. Absorption. All right. This is your absorption. Okay, so what we are saying, it is directly proportional to number of the atoms and it is directly proportional to the energy density, right? And absorption is directly proportional to the number of the atoms and energy density. So naturally here both the factors will get cancelled. So what we are getting, here we are getting B21 upon N2 and here we are getting B12 upon N1, and we already know that Einstein has proposed that B21 will be equal to B12. That is, both will have the equal value of the probability. So what we can say, if both the value are going to be equal, then in that case, this is going to be equal to N2 by N1. If B12 is equal to B21, then what we are getting, N2 by N1. That is stimulated transition upon stimulated absorption. So here you make absorption. It's not here, this is your absorption. So this is your correction that is required to make absorption. Okay, so I hope you have understood this, right? So what we are saying, if the stimulated is going to dominate over your absorption, then number of the atoms in the excited state should be more than the number of the atoms in the ground energy state, which is not possible according to Boltzmann distribution law of the atoms that we have just seen, right? So this is just a impossible things at the thermal equilibrium, but this is what is required to be broken if you require to have your gain of the light in the medium, right? The above equation indicate that the stimulated emission will dominate over the absorption when N2 is greater than N1. So what is the case? N2 is going to be greater than N1. That is, in the excited state, we have the more number of the atoms than in the ground energy state. And this condition is called the population inversion. This condition is called population inversion. So what we require is we have to reverse the number of the atoms, right? That is, we have to break the thermal equilibrium condition, and that will see how we have to break that thermal equilibrium position, right? So that we are going to get the population inversion and stimulated emission is going to dominate over the absorption, right? And we'll have the laser amplification. So that will come under the prerequisite of the laser, and that will be taken up in the next class. Thank you very much.